Welcome to lesson 27 on power system analysis. In this lesson we will discuss about the sequence networks. First we will start with an introduction, then we will talk about sequence networks for transmission lines. After that we will discuss the sequence network model for generators, and then we will discuss the sequence network model for transformers. After we have built these models for the various equipments, we will now go into the building up of the sequence network for power systems. Well, once you go through this lesson, you should be able to develop the sequence network for transmission lines, for generators and transformers, and finally you should be able to assemble sequence network for small power systems. Well, if you recall our previous lesson, we talked about symmetrical components and its advantages in analyzing unbalanced power systems. We also discussed about the sequence model for the loads. In this lesson we will be developing the sequence models for the other components such as transmission lines, generators and transformers, and finally we will be assembling these models to form small power system networks in sequence components. First we will take up the sequence network model for three-phase transmission line. If you recall, three-phase transmission lines have series impedance which consists of its resistance and the inductance for all the phases, as we have shown here as ZAA, ZBB and ZCC for the three phases. We have also considered the neutral wire or the earth wire of the system, which forms as the return current path in case of unbalanced system operation. Now, if you recall our lesson on transmission line modeling, you would remember that we have the ground wires or the earth wires at the top of the tower, and these ground wires are grounded at certain intervals, that is at the tower, at each tower by the tower footing resistance. So we have this return path which is made up of metallic conductor, the ground wires on top of the tower, and also the path through the earth. Here we are considering this ground as the ground wire or the neutral wire as the conductor on the tower. Now we have also, since these transmission lines, the phase conductors are near to each other as well as near to the earth wire, so we will also have mutual impedances between them, that is ZAB between A and B conductors, ZBC between B and C conductors, ZAC or CA between A and C conductors. Similarly, between each conductor and the ground we will have ZAN between conductor A and N, BN between conductor B and N, and CN between conductor C and N. We are assuming that the two ends of the line are represented by A, B and C and N on one side, and A dash, B dash, C dash and N dash on the other side. The voltage for phase A between neutral and phase A is VAN at the sending end side. We VBN, sorry, this should be VBN for voltage of phase B with respect to neutral, and VCN for voltage of phase C with respect to neutral. Similarly, on the other side we have voltage VC dash N dash for the phase C conductor on this side, and V dash N dash for phase B, and V A dash N dash for phase A. So, this is the complete circuit model that we have here. Current IA flows in phase A, IB flows in phase B, and IC flows in phase C in this direction, and IN is flowing in phase N, or that is the neutral conductor. Now, for this system we can write the relationships using Kirchhoff's law. If you recall, for phase A, if we want to write the relationship, what we will have is there is going to be a voltage drop because of current flowing in IA as IA into ZAA, that will be there, but because of current flowing in B also there is going to be a voltage drop which will be ZAB into IB. Similarly, for current flowing into C, there is going to be a voltage drop in this phase A, that will be ZCA into IC, and similar voltage drops will be there in the neutral conductor also, that is IN into ZNN will be because of IN flowing, but because of the other currents flowing, say current in phase A, we will have ZAN into IA which will be also a drop from this side to this, and BN into IB will be a drop in this, and CN into IC will be again a drop in this conductor. So, voltage from here to here can be shown like this. For phase A conductor, the current IA is flowing, and ZAB into IB is the drop here. Now, here what we have assumed is that the transmission line is fully transposed. Now, what does this really mean? As we have already discussed, that we do transposition to make the line symmetrical, that is, all the impedances over the complete distance of the line are going to be symmetrical for the transmission line, which simply means that ZAA is equal to ZBB is equal to ZCC, and the mutual impedances between the phase conductors are also going to be equal, that is ZAB is equal to ZBC is equal to ZCA. Similarly, for the mutual impedance between the phase conductors and the neutral also will be equal. So, ZAN will be equal to ZBN is equal to ZCN. So, this we are assuming for the transmission line, because most of the long distance transmission lines will be transposed lines. Even in case when they are not transposed, the asymmetry is not very large, and for most of the analysis purpose we assume the line to be fully symmetrical. Therefore, we have ZAB into IB, the voltage drop due to current flowing in IB, ZAB, which is basically ZAC. So, ZAC is equal to ZAB. So, we are writing ZAB into IC plus ZAN into IN plus ZAA into IA. This is the total drop from this point to this point. Similarly, for this current IN flowing on this conductor, the neutral conductor, we will have a drop ZAN IA in this direction, ZAN IB in this direction, and ZAN IC in this direction, and ZNN IN in this direction. So, if we look at the circuit like this, then we can write down the relationship as VAN, the voltage at this point is going to be equal to this voltage plus the drop here minus all the drops here, that is from here this voltage is plus this voltage plus this voltage, right. So, since we will be moving in this direction, therefore, these will be negatives. So, if we write like that, then VAN is equal to ZAA IA plus ZAB IB plus ZAB IC plus ZAN IN. This is this part, okay, plus VA dash N dash plus this voltage VA dash N dash minus this, because we have assumed current IN to be flowing like this. So, minus IN into ZNN. So, minus IN into ZNN minus IC into ZAN, which is ZCN basically. So, ZCN is equal to ZAN. So, we are writing everything in terms of A. So, ZAN into IC plus ZAN into IB plus ZAN into IA, that is taking care of these voltage drops with their directions taken into account. So, this is what we will get for VAN. So, if we take this VA dash N dash on this side, then VAN minus VA dash N dash is equal to, arranging these in terms of IA, IB and IC, we will get ZAA minus ZAN IA plus ZAB minus ZAN into IB plus IC, because this will be same for IB and IC. So, ZAB minus ZAN into IB plus IC plus ZAN minus ZNN into IN. Similar relationship we can write for phase B. So, we will have VBN minus VB dash N dash is equal to ZAA minus ZAN into IB plus ZAB minus ZAN IA plus IC in this case plus ZAN minus ZNN into IN. And similarly for the phase C, VCN minus VC dash N dash is equal to ZAA minus ZAN into IC plus ZAB minus ZAN into IA plus IB plus ZAN minus ZNN into IN. Now, we know that for the system IN is equal to the sum of all the currents, and the direction will be the reverse. So, minus sign will come here. That is, if we see here, IA plus IB plus IC will be flowing and the return will be through this. So, any unbalanced current will return through that. So, the direction of the current will be in this direction. Since we have taken IN in this direction as reference, so we have to use negative sign there. So, IN is equal to negative of IA plus IB plus IC. If we use this relationship, then finally we can write VAN minus VA dash N dash is equal to ZAA plus ZNN minus 2 ZAN into IA plus ZAB plus ZNN minus 2 ZAN IB plus ZAB plus ZNN minus 2 ZAN into IC. Now, this is what we will get by substituting for this IN minus of IA plus IB plus IC. So, we have eliminated IN and we get relationship in terms of IA, IB, IC. Similarly, for phase B, VBN minus VB dash N dash is equal to this term ZAB plus ZNN minus twice ZAN IA plus ZAA plus ZNN minus twice ZAN IB plus ZAB plus ZNN minus twice ZAN IC. And for phase C, we have VC n minus VC dash N dash is equal to ZAB plus ZNN minus twice ZAN IA plus ZAB plus ZNN minus twice ZAN IB plus ZAA plus ZNN minus twice ZAN IC. So, this is what we get for all the 3 phases. Now, we see here these terms ZAB plus ZNN minus twice ZAN is coming for the currents in the other phases. So, these are basically the mutual terms. So, for this is same thing is coming for IA and IB, whereas for IC the term is coming as ZAA plus ZNN minus twice ZAN. Similar terms if you see are coming for AN and BN. Here ZAA plus ZNN minus twice ZAN is coming for IA, and these terms are coming for the other currents. So, here again this term is coming for IB, and these 2 terms or the similar terms are coming for the other phase currents. So, we can write this term as ZS or the self impedance. So, ZS is defined as ZAA plus ZNN minus twice ZAN, and these terms as the mutual terms. So, mutual impedance terms. So, Zm is defined as ZAB plus ZNN minus twice ZAN. Now, with this definition of ZS and Zm, we can write this relationship as VAA dash is equal to VAN minus VA dash N dash is equal to ZS into IA plus Zm into IB plus Zm into IC, and so on for VBB dash, which is VBN minus VB dash N dash, again Zm into IA, Zs into IB and Zm into IC. VCC dash is equal to VCN minus VC dash N dash is equal to Zm into IA plus Zm into IB plus Zs into IC. So, this is how we can write this relationship. We are writing here VAA dash as VAN minus VAN dash and so on. Now, this is the impedance that we get for the transmission line in terms of self and mutual impedances. Here what we see is this is a symmetric impedance matrix and a 3 by 3 matrix with all the terms present in when we get the relationship between voltage and current for a 3-phase transposed line. Now, as we have shown earlier, we can get the symmetrical component impedance for the transmission line as A inverse ZP into A, where this matrix is the ZP matrix. So, if we do this, then we will get Z symmetrical component as Z0, Z1 and Z2, that is 3 independent impedances, only diagonal elements are there, all the off diagonal terms will be 0, which is the characteristics of a symmetrical component transformation when we do it for a symmetrical circuit. So, this is what we get, where we will have Z0 is equal to Zs plus 2 Zm, and Z1 and Z2 will be equal, and that will be equal to Zs minus Zm. So, what we find from this relationship is that the 3 networks we will have V0, V1, V2 is equal to Zs into I0, I1, I2. So, these relationships will be independent, that is we can write V0 minus V0 dash is equal to Z0 I0. Similarly, V1 minus V1 dash is equal to Z1 into I1, and V2 minus V2 dash is equal to Z2 into I2, that is we get 3 independent networks. So, 0 sequence network can be shown as V0 on this side and V0 dash on the other side of the transmission line, and an impedance Z0 which is equal to ZAA plus twice ZAB sorry Z0 which should be equal to Zs plus twice Zm, where Zs and Zm values are given here. Okay. this value comes if we do not have the neutral wires. So, when we have the neutral wire, then the value will be, this will be ZS plus twice Zm, and the current I0 will flow in this. Similarly, the positive sequence network will be independent, V1 on this side and V1 dash on this side, and the impedance will be Z1, which will be again Zs minus Zm. So, this is not ZAA, it should be Zs minus Zm, and similarly Z2 will be, for the negative sequence network, will be V2 and V2 dash on this side, and the impedance will be Z2. Current I2 will be flowing in this. I am sorry, this should be I2, not I1. So, this should be again Zs minus Zm as shown here. Z1 is equal to Z2 is equal to Zs minus Zm, and Z0 will be equal to Zs plus twice Zm. So, this is how we build the sequence network model for the transmission line, which consists of series impedances Z0, Z1 and Z2, and the three networks are independent of each other. These are passive networks. Now, we will take up the modeling of synchronous generators in terms of the sequence network. Now, this is a diagram which is showing the synchronous generator circuit model. We have the three phase voltages EA, EB and EC, phase sequence being ABC. So, here we have current IA flowing through phase A, IB through phase B and IC through phase C, and we have the impedances ZA, ZB and ZC for this. The neutral of the generator is grounded through an impedance Zn, and a current In in this direction is flowing through this grounding impedance. So, this is the basic circuit of a three phase generator. Now, since the generator is designed such that all these winding impedances, winding is symmetrically placed and uses the same wire and same number of turns. So, these windings will be having same impedances. So, it will be symmetrical, as well as the three voltages that will be developed in these windings will also be equal in magnitude, but they will be 120 degree out of phase from each other. When the generator works in normal balanced mode or symmetrical currents are flowing through it, no current will flow through this neutral impedance. But in case of unbalance, that is IA plus IB plus IC is not equal to 0, then in that case a return current will be flowing through this, which will be the current In flowing through the neutral. Now, we can build the sequence network model for the generators. Now, since the generator is designed to generate positive sequence voltages by the rotation of the rotor with the field winding excited, the voltages in all the three phases which are generated are equal in magnitude and 120 degree out of phase, and having the phase sequence same as the direction of rotation of the rotor, which is in this case shown as ABC phase sequence. So, the generator is designed to generate positive sequence voltages. So, we have a positive sequence voltage source for this model, and the generator has the winding resistance as well as armature reactances coming into picture. So, the total reactance offered by the generator can be seen, and that will be in steady state condition as the synchronous impedance of the generator, and that is also the positive sequence impedance of the generator. But in case of fault analysis, in most of the cases we are interested in finding out the currents immediately after the fault. In such cases, we, as we have seen from the generator model, we need to use the subtransient impedance of the generator, and also the voltage source here will be based on the subtransient or the voltage behind the subtransient reactance. This voltage, when for a loaded generator we had seen the terminal voltage is kept constant. So, depending on this current, the loaded, for a loaded generator we find out the generated voltage, and that voltage is taken as the voltage here in this case, and the impedance used in this case is normally the subtransient impedance. Normally the resistance of the generator winding is much smaller compared to its reactance, therefore, that is neglected, and generally the positive sequence impedance is taken as the subtransient reactance of the generator. So, this is the model for the positive sequence network for the synchronous generator. Now, negative sequence network. Normally, a generator is designed to generate positive sequence voltage, it does not generate any negative sequence voltage. So, there will not be any voltage source in this case. So, there is no voltage source for the negative sequence network. Now, what about the impedance? How do we find the impedance to the negative sequence currents flowing in the generator? Now, if you look at the generator and we want to find out its negative sequence impedance, then what we need to do is we can run this generator with its rotor short circuited, and we provide a 3-phase current which is in reverse sequence to the direction of rotation of the rotor of the generator. That means negative sequence currents will start flowing in this. Now, when negative sequence currents start flowing in the winding of the generator, what they are going to see? Now, since the rotation of 3 symmetrical currents which is flowing through this generator will produce a rotating magnetic field, because the phase sequence of the current is reverse to that of the rotation of the rotor. So, there is going to be a rotating magnetic field which will be rotating at the synchronous speed, but in the reverse direction to the rotation of the rotor. So, that is, there is going to be this relative speed between the two is going to be twice the synchronous speed, which means these currents which are producing magnetic field, currents flowing in this windings will produce magnetic field, and this field will be seeing two types of reluctances, one in the direct axis and another in the quadrature axis. That is, as it moves around, it will see a reluctance due to direct axis when the axis of the rotor coincides with the axis of the rotating magnetic field, and just some time after that it will see the reluctance because of the interpolar gap in which the field will have the maximum direction. So, it is going to see that reluctance after some time, and this will keep on repeating. So, what happens is it is going to see basically two reactances. One will be x q and the other will be x d. In fact, it will be x d dash, because this will be moving at that direction. So, transient reactance it is going to see. So, x d dash and x q is what it is going to see, and therefore, the negative sequence impedance seen will be an average value of that. So, it will be j x q plus x d dash divided by 2. But if we are talking of situation just after the if this generator has damper windings, then this damper winding is basically damper rods placed in the rotor pole faces, and which is short circuited. Since this rotor, there is a relative motion between the rotor and the magnetic field produced in the air gap by the current flowing in the stator winding, there is going to be voltage and therefore current flowing in the damper winding, because of which the damper circuit is also going to be active. In that situation, the reactance seen by these negative sequence currents will be very similar to that of subtransient reactance. So, therefore, we will get ZG2 double dash, that is subtransient reactance in the negative sequence, is going to be equal to JXD double dash, because XQ double dash is very much equal to XD double dash, because it is the damper circuit which dominates this reactance in the subtransient period. Therefore, we have the negative sequence subtransient reactance, which we will use when we are trying to find out the fault current immediately after the fault, and that will be equal to the subtransient reactance of the generator. Again, we would like to find out the zero sequence reactance. Now, again, zero sequence reactance can be found by supplying a zero sequence current to the three phases. Now, how do we supply a zero sequence current to the three phases? Since all the three zero sequence current means basically all the three phase currents are going to be having same magnitude and same phase. So, it is similar to connecting these three and supplying a single phase source, connecting it to a single phase source, then all these phases will have the same current and the same current with the same magnitude and phase flowing through them. Now, if that is the case, then the current will flow in through this, because if IA, IB and IC are flowing like this, then IN will be equal to IA plus IB plus IC, which is same as 3 times I0, and therefore, if we see the voltage drop from this point to this ground point, then this will be 3 I0 into Zn, which we can write as I0 into 3 times Zn. So, the impedance seen from this point to this point, if we look at the voltage drop, will be similar to an I0 flowing through thrice this impedance. So, this is what we will this is what we see here, 3 times Zn with an I0 flowing through it, and we will also see an impedance of the machine, which will be Zg0. Now, what is going to be the value of Zg0? Since resistance in most of the cases is very small, so we will be having basically the reactance which is coming, and what is going to be this reactance? Now, if we see the three phase currents flowing in these windings, which are 120-degree displaced from each other in space, will be having the same magnitude and same phase angle. Therefore, the sum of the MMF produced by them is going to be 0 in the air gap. In fact, in actual practice, this the three currents may not be exactly sinusoidal, so there will be some residual effect. But if we take the ideal situation where the three currents are sinusoidal currents and their phases are exactly same, then in that case the MMF produced by these three windings, currents flowing in the winding is going to be 0, and therefore, the impedance seen by these currents in this machine is going to be just equal to the leakage reactance of the windings. So, that is why we will get here Zg0 is equal to JXL, the leakage reactance. Since leakage reactance is much smaller than the subtransient reactance of the machine, therefore, we have Zg1 is nearly equal to Zg2, and this is going to be greater than Zg0, which is just equal to the leakage reactance of the generator. The typical values of Zg1, especially when we are using the subtransient reactances, will be of the order of 0.08 to 0.14 or something like that. So, Zg1 will be in that range. We are talking of this impedance in per unit. So, 0.8% to 12 to 14% is the value where the positive and negative sequence reactances will have, and Zg0, which is just the leakage reactance, will be of the order of 5 to 7%. So, 0.05 to 0.07 per unit. So, these are some of the typical values. It depends from machine to machine, these values may vary. So, this is about the synchronous machine model. Next, we will talk about the synchronous motor and induction motor model. Now, in case of synchronous motor, since we have is going to be exactly same as the positive sequence impedance of a generator. For induction motor, we do not have a voltage source, and we have just the positive sequence impedance of the machine, which is same as the winding impedance of the machine. Similarly, for negative sequence, there is no voltage source, but there is going to be the negative sequence impedance of the synchronous motor, which is going to be same as that of synchronous generator. In case of induction machine, also we will have the negative sequence impedance of the motor, and zero sequence similarly it will be similar in case of induction motor. In fact, in most of the power system modeling, synchronous motors, especially the large ones acting as synchronous condensers also, are sometimes modeled, whereas small induction machines are hardly ever modeled, and large induction machines in some cases may impedance of the machine. So, the network model are going to be as shown here. The positive sequence for the synchronous motor will have the voltage source, whereas there won't be any voltage source for the induction machine. The negative and zero sequence networks are basically the passive network having the negative and zero sequence impedance of the machines. Next, we come to the transformer model, the sequence model for transformers. Now, for transformers, as we have said earlier in our earlier lectures, we always use the per unit. In fact, for all the components when we work in power system, we use the per unit system, but for transformers it has to be used, otherwise you will have to keep on the voltage and current ratios always into account. We have seen that by using per unit model, the ideal transformer vanishes and only the impedances come into picture. Now, as shown here, the transformer has the winding impedance consisting of the resistance and the leakage inductance of the winding on the high voltage side, same thing, leakage inductance of the winding and the resistance of the winding on the low voltage side. This part is showing the core losses and this is showing the magnetizing current part. So, this is normally, as we have seen earlier, is the model for the transformer. Normally this current is much smaller and therefore this part of the circuit, the shunt circuit part of the circuit, is not included. So, this part is neglected, and also the resistance of the transformer winding is much small compared to the reactances. So, they are also neglected. So, what we have finally is basically the leakage reactance of the winding on both sides added together in per unit. In case of star delta transformers, as we have seen earlier, there is going to be a phase displacement of plus minus 30 degrees. Now, in case of star delta transformer, the normal practice which is used is based on ANSI standards, that American National Standard Institute standard, which says that for a star delta transformer, the high voltage side voltage is going to lead the low voltage side voltage by 30 degrees. So, this we can show by leading by 30 degrees like this, whereas the low voltage side is lagging by 30 degrees can be shown like this. So, here the positive sequence, in case of positive sequence voltage, the high voltage side voltage leads the voltage, low voltage side voltage by 30 degree, and the positive sequence network can be shown like this, where this is showing a 30 degree phase lead. In most of the cases we do not take care of the phase lead or lag also, but if one is interested, one can always take care of that. In case of negative sequence, again we will have the leakage reactance of the transformer, because this is a passive network, the reactance is going to be same. So, again here we have the reactance of the transformer, leakage reactance of the transformer, but in this case the high voltage side will be lagging the low voltage side by 30 degrees, because the phase sequence is reverse. So, in case of negative sequence, the high voltage side will be lagging by 30 degrees. Now, for zero sequence we have some complication in case of transformers because of the various types of connections which are used. If you look at this diagram, here we are showing this is phase A, phase B and phase C. This H1, H2, H3 are showing the terminal, H is showing the high voltage side and X shows the low voltage side. Similarly, small case letters are used for low voltage side and uppercase letters are used for high voltage side. Now, we are showing a current IA flowing like this, IB flowing like this and IC flowing like this. If these three currents are not balanced, in case of zero sequence, these three currents will be having the same phase, and so they will need a return path, and that is provided by the neutral connected to the ground. Similarly, same is the case here. This on the LV side, IA, IB and IC currents are flowing, and the return path is through this impedance Zn. Now, here there is, if the neutral is not connected, that is neutral is not grounded through an impedance or without an impedance, then in that case there is no return path available, which means this appears as an open circuit for the zero sequence currents. Whereas if the neutral is provided, there is this, all these currents will flow through this. So if you see IA0, IB0, IC0 will be flowing through this. So total current will be sum of these three currents which will be flowing through this, which is again same as 3I0. So instead of that we write I0 flowing through 3Zn. So the voltage drop from here to here can be represented as I0 flowing through 3Zn or 3I0 flowing through Zn. Same is the case here. In case the neutral is not grounded, then I0 cannot flow because there is no return path, that is all these currents cannot flow in this because they will need a path for it to, or a closed path for it to circulate. So when the neutral is not grounded, zero sequence currents cannot flow. Same is the case of the generators as well. If you remember here, if this was not connected, that is the neutral was ungrounded, then in that case you will find that this ZG0 is basically having this 3Zn also, and this 3Zn when it is open is infinite. So this will be open circuit and no I0 can flow. So here we find that in case there is no ground connection available, no zero sequence current can flow like that. Now let us see what happens in case of a star grounded and delta. In case of a delta, again the currents, zero sequence current can flow in the winding because these are having same phase. So it will appear as a closed circuit to this zero sequence current, and they can flow in the winding, but they cannot flow in the lines. So no zero sequence current can flow in the lines as such when we have a delta, but they can flow in the winding, and this is what makes transformer connections very interesting for zero sequence case. Now let us take the transformer with star grounded. Now this is the impedance of the transformer that will come into picture, JXL plus 3Zn. This is the impedance of the, Zn is the impedance of the grounding impedance on the high voltage side, Z small n is the impedance on the low voltage side. So this is the total impedance, and this, both these sides it will be connected because zero sequence current can flow on both sides because we have the return path available. Now let us see star grounded and star ungrounded transformer. In this case, on this side there will be a connection because zero sequence current can flow, there is a path, whereas on this side, that is the low voltage side, it is open because there is no path for zero sequence current to flow. So it will appear that this circuit is open, and the total impedance seen here will be JXL plus 3Zn. When we have a star both side ungrounded transformer, then this is certainly open on both the sides. So no zero sequence current can flow from either side into the transformer. Now if we look at star grounded delta connection for the transformer, this is grounded, which means zero sequence current can flow. So this is connected, and this is delta, which means it can flow in the winding, but it cannot go out. So it cannot go out means this side is open, but it can flow in the winding, so it is connected to the reference. So the connection is like this. Similarly, if we have star ungrounded delta, then this should be reversed. This is open because it is star ungrounded, and this will be closed because zero sequence current can flow in the winding. So, this side will be connected to the reference, whereas this side will be open. This is the reverse. I am sorry, this should be open because it is star ungrounded. Now, we have a delta delta transformer. Again here the zero sequence current can flow in the winding on this side as well as on this side. So, this is the impedance that is coming, and this will be connected to the reference as well as this side will be connected to the reference. So, this is how zero sequence network for the transformer is very much dependent on the type of three-phase transformer connections that we have. That is, a zero sequence current can flow in the delta winding, but cannot flow out of it, whereas a zero sequence current can flow through the inner star winding if the neutral is grounded. If it is ungrounded, it cannot flow, so it is an open circuit. So, here we have just explained this. The per unit sequence network of star delta transformer have the following features. The per unit impedance do not depend on the winding connections. That is, the per unit impedances of transformer that is connected star 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 delta delta star or delta delta are the same. However, the base voltage do depend on the winding connections. That is, if you make star or delta connection, then the voltage on the line side are going to change. They will be, if it is star, it will be √3 times the voltage what you will get with a delta connection. That does happen, but that is the line side voltages will become different. So, the base has to be chosen as the line side voltages on the two transformers. So, we have to use that way the base voltages of the transformer, which is dependent on the turns ratio of the transformer. A phase shift is included in the per unit positive and negative sequence networks. That is, plus 30-degree phase shift for a high voltage to low voltage side based on the American standard. That is, the positive sequence voltage and current on the high voltage side of the star delta transformer lead the corresponding quantities on the low voltage side by 30 degrees. For negative sequence, the high voltage quantities lag by 30 degrees the low voltage quantities. The zero sequence current can flow in star winding if there is a neutral connection, and corresponding zero sequence currents flow within the delta winding. They can flow within the delta winding, but not outside. However, no zero sequence current enters or leaves the delta winding. That is, it cannot come into the delta winding or leave out from the delta winding. So, this is a very important aspect in sequence network modeling for the three-phase transformers. Now, let us take a very simple example. For the system shown in figure here, we have a generator, we have a transformer, a transmission line, another step down transformer, and then we have a motor. The generator has its neutral grounded, whereas the motor has its neutral ungrounded, whereas the transformer T1 is a delta star grounded transformer, T2 is a star delta ungrounded, star ungrounded delta transformer. So, now we make the positive sequence network, EG1 and XG1 gives the network for the generator, XT1, which is again the subtransient reactance of the XG1 will be the subtransient reactance of the generator, XT1 is the leakage reactance of the transformer, XL1 is equal to ZS minus Zm, that is the positive sequence impedance. Normally, as we say, that resistance is neglected because it is much smaller. So, I am writing only the reactances. So, XL1 the positive sequence reactance of the transmission line, XT1 the positive sequence reactance of the transformer T2, and XM1 is the subtransient reactance of the synchronous motor, and EM1 is the voltage behind the reactance. So, this makes up the positive sequence network where the voltage source EG1 and EM1 are shown. Negative sequence will be same, except that all the impedances are replaced by their negative sequence impedances, and there is no voltage source in this case. So, this is basically a dead network. In case of zero sequence, we have the zero sequence reactance of the generator. The transformer, as we see here, is delta on this side. So, this side is grounded, means connected to the reference, this side star grounded. So, it is connected towards the line. So, this is what is shown, it is connected towards the line, and this side is connected to the reference. This is the reactance, zero sequence reactance, which is of the transmission line, which is equal to Zs plus 2Zm, and again this is the transformer, and this side is star ungrounded. So, this is open, this side is delta. So, the winding is connected to the reference. Then again here this is the reactance of the zero sequence reactance of the motor, which is placed here, and this will be the reference. So, this is the zero sequence network. So, this is how we can assemble the sequence network for various components to build the sequence network for the power system. So, depending on the transformer, the zero sequence networks do change, whereas the positive and negative sequence networks are very similar to each other, except that negative sequence network does not have any voltage source in it. So, zero sequence and negative sequence networks are basically dead networks. Only when there is an unbalance, then these networks get connected to the positive sequence network, and there is current flowing through them because of the voltage sources available in the positive sequence network. So, with this we finish today, and we will take up the unbalanced fault calculation in the next lesson. Thank you.